Hello guys, let's do today something new and we are going to explore can we do CUDA programming in Python. So as we see, this C++ is necessary to run CUDA on a GPU. So here is a C++ program to run to basically add two vectors, and what we need to understand is what are the concepts involved here. First of all, understand the concept of parallel programming, and basically its ability to run bunch of threads simultaneously at the same time rather than doing serial programming. Understand what is a kernel function in CUDA. So that's what you see in the C++ program with the global keyword. So that's the function that will run on the GPU actually, while the rest of the code runs on the CPU. Then you have understand the concept of host memory versus device memory, and then you understand the concept of copy to device. And what does copy to device means? What is a device in this here? In this case, it is a GPU. Basically, it's a shorthand for GPU. And then understand how will we launch a kernel. So kernel is basically launched with its usually specific syntax, like triple angle brackets in C++ versus just the slightly different syntax in the Python side. So that's all you need basically to understand what is this CUDA programming all about. So if you see, the parallel programming has been around for a long time, even before CUDA. So the idea of threads, and for example the POSIX threads and running multiple codes of execution at the same time on different cores was the even happens on a CPU. So that's your parallel programming already. So what's so different about the parallel programming in CUDA? Because CUDA gives you thousands of cores rather than tens and twenties. So when you have thousands of cores, you can pretty much, for example, we are adding two vectors of 1 million elements each. So we can pretty much add each element of a vector, each index from 0 to 1 million minus 1 on a with a different thread, which is a slightly different concept than doing it on a C++ POSIX thread. So now we talk about what do we need to run CUDA in Python. So as you know, the C++ is kind of going away, and we don't need that. So as you can see, I'm running a CUDA program, Cuda Python program. After translating, we are going to run it now, and then it says Python 3 Cuda1.py, and it ran absolutely fine. And just to show you the program again, what do we have is Cuda1.py, and so I changed the initialization so that very easy to verify that we are actually adding these two arrays index by index. As you can see, that one is initialized to 1 and this one is initialized to 0.5. Here you say also 1, not actually, not, because that one is commented out. So both are initialized from 1 to n, and both have been initialized to, in this case, the default value is, I guess, when we run, so let's run it again. So 2, so 1, 2, 3, so that is the default initialization. There's a Python rule, as you can see. So 1.0, 2.0, 3.0, 4 until n.0. So that is why each corresponding element of A and B is added up. That's why 1.0 and 1.0 again is 2.0. That's why the next one is 4.0. So that is your Python CUDA program, and pretty much all the concepts are same. As you can see, and just like the C++ program, it has vector add function, except it has a decorator of cuda.git, but that's very easy for you to add. So you have your CUDA kernel function as it is, just like in a C++ program, and then the rest of the code is, you can see, is pretty much the same. The block index, you are basically calculating here the global thread index. So remember two very important concepts. So let's do the VI here. on cuda.1.py. Just I'm going to add a comment here so it makes you, it's kind of clear for you guys. So what is I here? So most important thing is to realize now we have to use Python style comments, that this is understand the global thread index. So that's what is happening here. Basically you're calculating the global thread index, and there's also a concept of local thread index. So local thread index, local as in local for each block. So if you go, this is the block number, there's a number of threads in each block, and this is the nth thread. So in this case, since the vector size is 1 million, as you can see, we will have 1 million threads total, and each thread will do just one thing, which is ci equal to ai plus bi. And so here ith thread, think of this I as in like the thread number. So now you see why it was so easy to translate your C++ program into the corresponding Python program, because the function vector add is as it is, as we can see, pretty much the same function except its Python translation, which is the Python syntax. So you don't have to declare the type of the variables and things like that, and rest of the 1 million elements size is same. And understand how did we initialize the HA, HB and HB, just like we had done in C++ equivalent, and then allocate device memory we had in C++ code as well. We were doing things like if you see in C++, what we were doing the this is the Python version actually, not the C++. So I think there also we were having Cuda malloc or something like that, and then the rest of the pretty much like one-to-one translation. You are having vector add. You can see that instead of grid notation in C++ to run your launch your kernel, you just have to call here vector add as by this notation, and you basically pass all the three arrays and the size, copy result back, copy to host, and you're done. So it's pretty interesting, and you can see that the translation was pretty much one-to-one. So now if I were to show you the C++ equivalent, let's go and see the C++ equivalent. So we would so this is the C++ equivalent, where the C++ has its own weird Cuda syntax, where function is pretty much the same except that you put a global saying there's a Cuda kernel. Actually it should be called Cuda kernel, which itself is a kind of a confusing concept for a newbie, because kernel, if you think like OS kernel, no, it's not a OS kernel, it's just a function that runs on the GPU. So Cuda kernel function, let's call it. And you see you have to declare variables, of course, but pretty much the same code. But and the host memory was allocated using malloc, actually not Cuda malloc. Cuda malloc you will be using for device memory, the memory on the GPU. So DADB, and then you just basically copied it, Cuda mem copy, copy it from host memory to device memory, and you define your kernel config. You have 256 threads per block, and blocks per grid is basically making sure that enough threads are basically allocated, in this case 1 million. So that's why remember this trick about making sure that you get every thread gets. So once we know there's so many threads we will need, so and then you say threads per block, so that means it's basically block calculation, how many blocks do we need so that we can have enough number of threads. And then you have launch kernel, and launch kernel syntax is slightly different from the one in Python, but it's pretty much one-to-one except for the weirdness of bracket index versus what we had in Python case, and copy result back. But copy result back, so you have two Cuda mem copy calls, actually three. In the beginning you had copy to device, then copy result back, and verify instead of free for the device memory you have to call Cuda free. So anything that happens on the GPU you do Cuda malloc, Cuda free, but for copy to device you say Cuda mem copy, and you can do back and forth, device to host, host to device. So that's it, it's very easy. but we are past C++ now, in this day and age where chat GPT rules, and the traditional programming has taken a back seat, because you can only do the string reverse so many times, because and then there's no fun in that. And the progress has moved now, as many pundits have already proclaimed that we are into the next era of computing, and that computing is AI and GPUs and model training, inference, and neural networks behind neural network architectures, understand Python, understand PyTorch. So now let's look at the Python code again. So where are we? We are actually in non-GPU machine. Now let's go to the GPU machine. So this is GCP GPU machine. It has a GPU. You can see, actually, if you do LSPCI, you could see that it has a, see here, NVIDIA corporate. Look at that. I have Tesla T4 GPU. So it's a GPU machine. There are also a bunch of other CUDA command that you can actually verify. I think SMI is one, and NVIDIA SMI, as you can see, it gives you, if it is Tesla, see Tesla T4 GPUs. This is a GPU machine, and that's where I thought, you know what, why are we running CUDA programs in C++? C++ is old school. We're going to do it in Python. So that's when the idea of running CUDA through Python came to me, and lo and behold, it turned out to be very easy and very pretty much one-to-one correspondence concept-wise. The concept of a kernel function, which is a function that runs on GPU, and then pretty much making sure that if you have, in this case we are doing a vector add, so we have n element with 1 million elements of vector add, and for each thread we do one addition. So we are pretty much running 1 million threads, you could say, and they are run on so many number of blocks. You can see the block calculation here, and that's what we pass in the vector add call, which is a launch the kernel. So in principle, it's not necessarily one kernel. There could be many kernels running, because you run many kernels through streams. So understand that other concept of a stream and things like that on a CUDA GPU. And then you see device memory, copy to host, and then you had a copy to device APIs. So understand that this is what you need to do. Make sure Numba is installed. We can do a Numba -s. If you have Numba installed, you're pretty much in luck. You can just run your CUDA programs in Python. There's no need to have the C++ and all those. As you can see in this Python program, we did NumPy we imported only NumPy and Numba. From Numba import CUDA, from NumPy import NP, and we use NP to allocate traditional arrays, basically, pretty much, and that's one, and it was never called again. So the host memory, those arrays A, B, and C, they were allocated using NumPy. So NumPy. So understand CUDA.jit, the traditional, the just-in-time compiler. I mean, basically it's a decorator function, it seems. So this is how in Python you do decorative function. Understand Python decorator, but probably you don't need to, as long as you can just simply do a @CUDA JIT, and your kernel function is pretty much same. Focus on that one and how it is called. And in theory, you can have bunch of kernels. Don't think that there's only one kernel running on the GPU. Kernel is basically the function that runs on GPU. So with that, you should be ready to go, and don't have to worry about C++. You can simply do your Python CUDA programming in Python, your parallel programming in Python. As you can see here, 1 million threads are running, and each running on its own thread, which is inside a block inside the GPU, and GPU has number of grids. Actually, I think, yeah, so the grid is like a city, and the block is like, the blocks in the city, and then each block has like so many threads. So that's why you see threads per block. He has this threads per block, right? Then he calculated blocks per grid, how many grid I would need. So you have to, that's why this global thread index and all those things. So CUDA, so here you see this is number of threads in a block, this one. the second one, which is a little bit confusing. The rest is simple. You have the block index, you have the thread index, and this is just number of threads in block. So I'll leave you guys alone and just make sure that you understand that you can also run Python through CUDA through Python, and you don't have to worry about C++ and things like that, because we are past C++ age, I guess, with Python's beauty and the easiness of programming. Everybody's moving towards Python. And with that, I leave you guys alone. I'll see you in the next video. Until then, bye bye.